This is lecture 2 for Chemistry 312. This lecture is on nuclear properties. The readings associated with this lecture can be found in Modern Nuclear Chemistry, Chapter 2, and Nuclear and Radiochemistry, Chapters 1 and Chapters 2. In this lecture, we're going to discuss some properties of the nucleus. We're going to really focus on masses, discuss how the mass of a nucleus will differ from the mass of the component and constituent neutrons and protons. Talk about binding energies as a way of describing how stable a nucleus is. We'll start to discuss reactions, and for this case we're going to talk about something called the Q value, which is reaction energy for nuclear reactions. And then we're going to start discussing the concepts that nuclei have shapes. One way of evaluating nuclear properties is to examine some systematic trends in data. And one data that's readily measurable is mass. We can evaluate atomic mass, and most of the mass is contained within the nucleus, so that should shed some light on nuclear properties. And what we're going to find out is that some aspects of the nucleus, like mass, shape, size, stability, follow patterns, and we use these patterns to develop models. Some of these models are average properties, and we're going to call these more macroscopic models. Some models are going to have some details in the nuclear properties. These are going to be more microscopic models. And today we're going to introduce a more macroscopic model, the liquid drop model. But an example of some trends that are observable in the nuclei from some very simple data presented here. If I were to look at the number of stable nuclei from the chart of the nuclides and evaluate the number of stable nuclei based upon whether or not they have an even number of protons and an even number of neutrons, I get this interesting result that out of all the stable nuclei, 160 have even numbers of neutrons, even numbers of protons. 53 have an odd number of neutrons and an even number of protons. About 49 are reversed, so an even number of neutrons, an odd number of protons. And there are only 4 stable nuclei that have odd number of neutrons, an odd number of protons. So from this very simple observation, we can start exploring nuclear physics and nuclear properties by saying that the number of protons and neutrons are important, and they actually dictate some behaviors within the nucleus. As an aside, we can examine the 4 stable odd-odd nuclei. Here's the first part of the chart of the nuclides. Odd Z elements, hydrogen, lithium, boron, nitrogen, are listed here. So one odd neutron, odd number of proton, stable isotope is hydrogen-2, deuterium. The next, lithium-6, 3 protons, 3 neutrons. If I look at this trend, I'm going to guess that it's boron-10, and I would be right, 5 protons, 5 neutrons. And the final one, if we follow this line up, nitrogen-14 is our final stable odd-odd nuclei. So, a way of evaluating trends in nuclei is simply to evaluate the mass. The mass is a property that can be relatively easily measured. So one of the terms that we're going to explore is something called the mass excess. And this is the difference between the actual mass of the nucleus and the expected mass from the atomic number. Quite simply, it's just the delta, which is mass excess, is equal to m minus a being the atomic number. Now, one thing I wanted to find about the atomic number is that it's based upon carbon-12, where carbon-12 is defined as 12 atomic mass units. And we can get some information from the mass excess. If the mass excess is negative, then the isotope has more binding energy than carbon-12. So you can actually use carbon-12 as a reference point for evaluating nuclei. Okay, so one thing here, we can talk about mass, something, the property of the nucleus, how much excess mass it has in comparison to what we would expect just from the number of neutrons and protons. This is a pretty simple equation where m is the nuclear mass, a is the mass number, and the unit here is in MeV. Now, here's something, MeV is an energy unit, yet we're talking about mass, And how do we get away with that? Well, we do a relativistic calculation. We exploit E equals mc squared. So energy and mass are related through this equation. So here's an example of what we can evaluate with mass excess. The mass of sodium-24 is 23.990962, etc. atomic mass units. So m minus a, this value minus 24 is equal to negative 0.00903 atomic mass units. If I use this conversion, 1 atomic mass unit is equal to 931.5 MeV, mega electron volts. I run through this equation, and I get a mass excess of negative 8.42 for sodium-24. And I can calculate this value for just about every isotope. The data is available, and we'll discuss this later in the lecture. Masses can be used to evaluate reaction energetics. First, from this, we need to determine nuclear masses, and we can get this information from atomic masses, because the atomic masses are just composed of the mass of the nuclei and the mass of the electrons. So we can utilize this relatively straightforward equation, where the nuclear mass is equal to the atomic mass minus the electron rest mass and the total binding energy. Now, the total binding energy is a very small term. Here's an equation here, and I want to point out that the unit is in electron volts, where units for mass of nucleons are in mega electron volts. So the total binding energy of electrons is small compared to the total mass. Now, in a nuclear reaction, we should get a mass change between the parent and the daughter, and this can be expressed by the energy Q, the Q value in an equation. So let's go through some decays and give these examples. So let's talk about beta decay and the Q value associated with beta decay. Beta decay is listed here, where I have an isotope. A neutron is converted to a proton, so Z increases by 1. An electron, a beta particle, is emitted, along with an antineutrino and some energy. So here I'm just writing Q as part of the equation, like we might do in chemistry. Now, this is charge balance between the number of protons and the number of electrons. If I add one more proton, it now becomes positive. But here's an extra electron, and what we're going to do, we're going to say that this electron mass plus this charged Z plus 1 nucleus, we're going to say that that's approximately equal to the atomic mass. It's neglecting the binding energy of this electron, but we've already said that that's pretty small. So the Q value for this reaction, if I just looked at this and solved for Q, and we're going to say the mass of the neutrino is 0, or excuse me, the antineutrino, this is nothing more than the mass of the parent minus the mass of the daughter will give us Q, and that equation is listed right here. And I've already listed this equation directly in binding energy. So let's use an example. The decay of carbon-14 decays by beta to nitrogen-14, an emission of a beta particle, an antineutrino, and Q. The energy is just equal to the mass of carbon-14 minus the mass of nitrogen-14, or the mass excess of carbon-14 minus the mass excess of nitrogen-14. I'm going to look at the Q values, and here's the URL where I grab these Q values from, and I get a beta decay Q value of about 1.5 MeV. Let's evaluate a positron decay. This is kind of the opposite direction of beta decay. So I have a nucleus here, which is Z going to a Z minus 1. This is now negatively charged because I've taken a proton here, converted that proton to a neutron. From the atomic point of view, I have an extra electron. It also emits a positron, which we're also going to count as an extra electron. It's an antimatter of the electrons, so it's not 100% correct, but fundamentally it has the same mass as an electron. So we need to consider two extra electrons, this extra atomic electron and the emitted positron. Electron mass is 0.511 MeV, So in total, we have a little over 1 MeV of mass that's contributed by the electrons. So the Q value is equal to the mass excess of the parent minus the sum of the mass excess of the daughter plus 1.022 MeV. As an example, we'll look at the positron decay of niobium to zirconium-90. And the reactions listed here, where we get a positron plus neutrino. We use the mass excess equation, and this becomes, we get the data from the mass excess, and we get a Q value of a little over 5 MeV. Electron capture, this is similar to positron decay, where the nucleus captures an electron and a proton is converted to a neutron. But in this case, the electron is an atomic electron. So let's write it as we have a charged atom plus one of its atomic electrons. This is going to Z-1 plus the neutrino plus Q. So if we solve for Q, we can put these two together. We can put the parent and the electron together. That becomes the atomic mass. So this becomes nothing more than the mass excess of the parent minus the mass excess of the daughter. And as an example, we'll look at the decay of bismuth-207 to lead-207. Q is just equal to the mass excess of bismuth-207 minus that of lead-207. I can look these values up in the URL that was listed on the previous page, and I get a Q value of 2.4 MeV. The mass excess for alpha decay can be solved using these equations presented here. Let's look at the decay of an isotope defined by A and Z. Since alpha decay is the emission of a helium nucleus, A decreases by 4, Z, where the Z of helium is 2. So I get the equation where the parent is AZ, the daughter is A-4, Z-2, plus the alpha particle, which is the helium nucleus, plus Q, which is the energy. So let's have an example where we look at the alpha decay of americium-241 to neptunium-237. We can use mass excess tables. I'm going to show this from an example of the nuclear Wallet mass excess table. There's also a Q value calculator that I'll show later in the lecture that we can use to calculate this. And you could actually use data from the table of the isotopes. If you looked up americium-241, the Q value would be explicitly presented. All right, so if I rearrange this equation and substitute the nuclei for the nuclear with the mass excesses, I get Q is equal to americium-241 minus the sum of neptunium-237 and the helium nucleus. So the data for americium-241 is here. Our data for the neptunium is here. And our helium data is listed here, where the mass excess on the table is given here by delta, and these values are in MeV. I substitute into this equation, I solve, and I get a little over 5.6 MeV. And if I go to my chart of the nuclides, I see that my alpha decay energies for americium-241 are close, but not quite. In fact, the alpha decay energies, what we're going to learn, the alpha decay energies are always lower than the Q value, because the Q value not only incorporates the alpha decay energy, but it also talks about the recoil of the daughter. And we'll talk about this in more detail when we get to alpha decay. Now we've just given Q value estimations for a range of common decays, but in fact the Q value can be estimated for any reaction we choose, any sort of nuclear reaction. And the way one can do this is write up the reaction and just include Q as you would as part of the equation, and then solve for Q. So here's an example of an alpha particle bombarding iron, making cobalt and a proton. So if I solve for Q, it's just equal to iron and helium minus the masses of cobalt and the proton. I've actually taken this data, thrown it into the Q value calculator, which the URL for the Q value calculator is listed here. and I get a Q value of minus 3.24 MeV, which means that this reaction doesn't occur unless I throw energy into the system. And we'll discuss this in more detail when we talk about nuclear reactions. So there's a wealth of information that you can mine to get Q value and mass excesses. Table of the isotopes have both for certain decays. The Q value calculators, and we'll discuss this in class. I'll give an example. I do want to show you that you can actually throw in an isotope and use the Q value calculator to calculate any reaction that occurred with that isotope. And there's also a whole list of atomic masses of isotopes at this URL. And here's some examples of Q value computations that involve both masses and mass excesses. So here's an example of 24 sodium undergoing beta decay. We use the masses. We use our conversion factor of 931.5 MeV per AMU. And we get a Q value of 5.5 MeV. And from the mass excess, we're also at 5.5. We're a little bit different. This is 5.516 from the mass excesses. We're from the MeV for the AMU. We get 5.5154. There's slight differences in the data. And to be explicit, sometimes you may just want to list where you got your data for doing your computations. And then there's another Q value computation below for the EC electron capture of sodium-22. We do the same thing, one through the masses and then one from the mass excesses. And we see that this data is very similar. Okay, now that we've explored some energetic terms, let's figure out what other data we can evaluate from these energies. And one is fairly common, something called binding energy. Now, if I look at a nucleus, I know that it's composed of neutrons and protons. Yet the mass of that nucleus is often very different than the mass of the constituent nucleons and protons. So if I were to sum up all the neutrons and protons in the nucleus and evaluate the mass from that sum, it would actually be different than the actual mass of the nucleus that I measured. So this is a way of saying, well, this would be the energy released if the nucleons came together and formed the nucleus. And what this term is called binding energy, and it's equal to, as I said, the number of protons in the nucleus times the number of neutrons in the nucleus times the nuclear mass minus the actual mass of the nucleus. And what we actually evaluate is the binding energy per nucleon. So you can think about all this extra energy in the nucleus gets spread around per nucleon. And this is a way of measuring relative stability. And over here is a figure of our binding energy per nucleon. So here's a plot of the binding energy as a function of A, of mass number. And we see this trend is that it peaks, it starts very high, it starts very steep slope initially. It peaks around iron and then it decreases. And there's a few data points that we can get from this. One is that there's this very high slope here that shows that you can get a lot of energy if I were to take lighter elements here and force them together. That's fusion. And this is the reason that fusing hydrogen to make helium is so exothermic. It's such a large release of energy. In fact, from this, I could see that stars, I can fundamentally go all the way up to iron, taking lighter elements, fusing them together, getting a higher binding energy per nucleon, and releasing energy into the system. But this is also responsible for fission. If I have something like uranium-235 here, and I split it into isotopes that are lighter, I go up this binding energy curve with the release of energy. So this curve explains fission, it explains fusion. It also explains where this maximum point is with iron. There's a large abundance of iron elements around iron in the universe, and some of it's explained by this high peak in the binding energy curve. Right? We can also use some of our calculations to explain some trends that we see in nuclear properties. So for instance, we know that uranium-235 can fission with a thermal neutron, while uranium-238 doesn't. Let's try to use some energetics to explain this trend. Here's the general reaction. We can calculate the Q value. Here's the data that one could use. Again, there's a number of data sources one can evaluate for this. So here's our general trend. We take an isotope, we add a neutron, and the Z doesn't change, but the A increases by 1. We said uranium-235 fissions, but uranium-238 doesn't. The Q value for this reaction for uranium-235 going to uranium-236 is given here, and the Q value is 6.5 MeV. For uranium-238, it's positive, but it's a little bit less. It's over 1.5 MeV less at 4.8 MeV. Uranium-233, which also fissions, is again above 6.5 MeV. When we evaluate this, we find out that fission requires, to get over the fission barrier, between 5 and 6 MeV. So we can see that uranium-238 won't fission, while uranium-235 does, and uranium-233 does. And when we discuss fission, we'll actually talk about why this occurs, and a lot of it's driven by the unpaired neutron. Uranium-235 and 233 have an odd number of neutrons, and I add an extra neutron, those neutrons pair. We can now take some of this fundamental information and develop a simple nuclear model. And the simple nuclear model we're going to use to calculate binding energy. Some of the concepts of the model will say that the volume of the nuclei are basically proportional to the number of nucleons present. Nuclear matter isn't very compressible, and this is the basis of an equation for nuclear radius. We'll also say that the total binding energy is fundamentally proportional to the number of nucleons present. There are some variations in this. Some of this is driven by something called a saturation characteristic, where nucleons can only interact with a small number of other nucleons, basically those in the neighbors. So if we look below here, we're going to have some differences whether or not the nucleon is sitting in the middle of the volume, because it can interact with a lot of different nucleons, or whether it's on the surface, because it's unable to interact with nucleons that are not above it on the surface. So basically, we're going to use these very simple concepts to develop something called the liquid drop model of the nucleus. And we're going to base this on, we'll use our data to develop some terms, but the variables will be the number of neutrons and protons in the nucleus and how they arrange themselves. There's a URL from Wikipedia that actually has a reasonable explanation of something called the semi-empirical mass formula, which is the basis of this liquid drop model. So here's the liquid drop model as written, where the binding energy is equal to some constants times some terms that are just variations in the number of neutrons, the number of protons, and the sum of the neutrons and protons. And all I really want to do with this equation is look at the different terms. So let's talk about and how these terms are used to develop this model. So the first term here, this is our volume term. It's the dominant term in this equation, and it's basically saying that the binding is proportional to the number of nucleons. This value here represents symmetry energy, which is greatest for nucleons with equal number of neutrons and protons. As we go to other terms, this term here, the second term, it decreases the binding energy. We subtract this term from our first volume term. And this is a surface term. This discusses nucleons at the surface. They're unsaturated. They're not fully saturated with nucleons, so they cannot express and incorporate their binding energy completely. This decreases in importance with increasing nuclear size. Our third term and our fourth term, these are Coulomb energy terms, and these represent electrostatic energies that arise from Coulomb repulsions between the protons. So the more protons I have in the nucleus, the more they're going to try to repel each other. So this decreases, while this fourth term is a correction term for the distribution within certain boundaries, and that adds a little bit to the binding energy. And this final term is the pairing energy. And this is just from the fact that there's some trends that are observed where neutrons and protons, if they are distributed into pairs, they have slightly better energetics, and this adds to the binding energy. The liquid drop model can be used to compare with data and evaluate some trends that are evident in the nucleus. So for instance, here we're going to discuss some comparison of experimental and calculated binding energies with the calculations done with the liquid drop model. What's evident here is from what we plot, this is the difference in the binding energies based upon number of protons and number of neutrons. We see that there are some variations at some different points. Here we see the values, and they wind up being 2, 8, 20, 28, 50, 82, and for neutrons, 126. What this tells us is that the liquid drop model has some limitations. It doesn't describe the nucleus in its entirety, because the nucleus, as we're going to find out, is not a liquid drop. What we are going to find out, these numbers here are what are called magic numbers. And when we go to the shell model, we're going to see that these numbers are points where the nuclear shells become filled, very similar to electron shells being filled. Another way of demonstrating trends in data is with mass parabolas. This is a route of establishing which isotope has stable constituents. What one can do, you can plot some energetic term, and this is basically differences in energies against Z for a given A. And here's some data, mass parabolas, for A equals 75 and A equals 157. So the 75, the Z's for the 75 are listed here. The A's for the 157 are listed here. These are odd A, and what we see for the odd A's, there tends to be only one beta-stable isotope, and this is nearest the minimum of the parabola. Here's a mass parabola for an even A isobaric chain, and this is taken from the table of the isotopes. This is for 156 isobar, and we see that for even A nuclei, there are 2 or possibly even 3 beta-stable elements. Here demonstrates the 2 beta-stable isotopes, gadolinium and dysprosium 156. Now we see that the energetics here, the dysprosium is at a higher energy than the gadolinium, but in order to decay would have to pass through this terbium, which is at a even higher energy. So the dysprosium would have to somehow gain energy to go to this terbium and then go down. So this is basically a valley in this this distribution. So this is why we can get 2 beta-stable isotopes, even though their energetics between these two are different. One of the other terms that we can evaluate from some of the data we've already looked at is nuclear radii. Here's an example of a very straightforward equation where the radius of a nucleus is just equal to r, which is a value here of 1.1 to 1.6 Fermi, times a to the 1/3. Again, this goes along with what we discussed with the liquid drop model, that nuclear volumes are nearly proportional to nuclear masses. And from this we can get very easy routes for determining something about the radius of a nucleus. A nuclear radii can mean different things. It can talk about, well, the actual force on the nucleus. If we think about a nucleus, there's protons in there. So that may give us information about the charge field of the protons, and possibly even information about the distribution of those charges within the nucleus. One way of measuring the nuclei is to quite simply take a target material, shoot particles at it, and see how those particles behave. And here's an example of an experiment where one takes a particle, shoots it at a nucleus. We look at the way the particle behaves after it interacts with the nucleus. We can get parameters that we can wind up talking about the area of closest approach. So what this does for us is evaluates how close a particle can get to a nucleus. There's a URL link here that describes this in a little bit more detail. But basically, we can evaluate a distance of closest approach. And as an example, using this equation, where we talk about the kinetic energy of an alpha particle, the initial kinetic energy, listed here, and the final kinetic energy being measured, is the difference between that includes a term that describes the distance from the center of the nucleus. So it's the closest approach, and it's a way of measuring the nuclear radii. If one does this, we see that we get nuclear radii of 10 to 20 femtometers for copper and 30 to 60 femtometers for uranium. This doesn't mean that there's variations. What it really means is the differences in this closest approach will depend upon the energy of the particle that we're using. So fundamentally, any positive charged particle can be used to probe the distance. This nuclear attractive forces become important relative to the repulsive forces as a particle gets closer to the nucleus. Neutrons can also be used, but they require high energy. Neutrons, as they're neutral, they will not vary based upon the nuclear charge, so they will ignore the Coulombic forces. But you need high energies because the wavelength of the neutrons at high energies start becoming similar to the wavelengths of the nuclear radii. But at high energies, the nuclei are very transparent to neutrons. The cross-sections are small, so the probability of an interaction in which you can measure some nuclear properties related to size with neutrons at high energies. Electron scattering is also pretty useful. And in fact, with electron scattering, you can get information on the details of the nucleus. High energy electrons can yield information about the charge distribution within the nucleus. So you can actually get data on how the protons sit within the nucleus. Some other results that come out of this is that the radius actually can be described as a half density radius and something called a skin thickness. So let's go over that in a little bit more detail, because this is a way of describing how the nuclear matter behaves within the nucleus. One can take the scattering data and develop a very simple model called a square well potential. The square well potential is provided here. This is for protons. This is the square well for neutrons. The data through an evaluation actually fits better from something called a Wood-Saxon potential, where you don't have this square drop-off, but you have a slight change in density over the radius. The Wood-Saxon potential is listed here. Where I have this term is the potential at the center of the nucleus. There's a constant involved. R is the distance at the center from which the potential drops to a half. And what I can do at any given distance, I can measure this potential. What comes up from the square well potential is I get radii of 1.35 to 6 femtometers, where the Wood-Saxon gives me something a little bit less. The The Wood-Saxon also describes something called this nuclear skin thickness. This nuclear skin thickness is pictured here. What we see is that the density of nuclear matter at the center of the nucleus is higher than at the very edge. One can use the Wood-Saxon potential to calculate what fraction of nucleons live in this skin region. And this data is provided here. And as we see, as we increase A, the percentage of nucleons that are in this skin region begins to decrease. There's a density that we can look at where the density of the nuclear density at a given radius is equal to the density in the center divided by this term here, and this is our Wood-Saxon potential term. What this looks like is pictured here, where we see that we have a density that drops off at a given distance and eventually goes to 0 for nuclear matter. Within here, we can describe a half thickness. So I have a radius in which the density drops from the center to 50%. And then I have a skin here where the density goes from 90% to 10%. So not only do now I have a number of different ways of describing the nucleus. I can talk about its radius that we can measure with something as simple as the A, or calculate with something as simple as the A. Now I have a little bit more detail where I can talk about a half thickness and a skin thickness. So now the nucleus is getting a little bit more detail and a little bit more shape. Right, we'll end this lecture talking about some quantum mechanical terms that are useful from the nucleus, and we'll actually show that some of these are based upon the nuclear properties and how the nucleus builds itself up. One term is spin, where electrons, we've already discussed that they have spin. In our first lecture, we gave a table on this, but electrons have spin, protons and neutrons also have spins, and these spins are 1/2. What we're going to learn when we go to the shell model is that, like electrons, protons and neutrons can fill shells. They fill these shells, and these shells have different orbital angular momentums. From chemistry, we know that electrons can have s, p, d, f. In the nuclei, they can go to g, h, I shells. We also know that spin of even A nuclei, if I would go by inspection in the chart of the nuclides, they're either 0 or integers. And a spin of odd A nuclei are half integral, 1/2, 3/2, 5/2. All nuclei of even A and even Z are 0 spin in the ground state. Nuclei also have magnetic moments. We know this from anyone who's done nuclear magnetic resonance to evaluate chemical compounds, exploits the fact that protons and carbon have spins that we can measure by nuclear magnetic resonance. So proton, carbon, and carbon-13 are used. The way that we can evaluate nuclear magnetic moments is listed here. And a lot of this comes from splitting. There's a number of experiments, atomic beam methods, resonance techniques. The bottom line is that the data, the peaks in the data are split, and the split is based upon the spin of the nuclei. For some of these spins, they can be, for instance, twice the spin plus 1. And this is something that we're familiar with from NMR spectroscopy. You should take away from this is that we can evaluate this nuclear property, this magnetic property, based upon experimental data that we can measure. A final term that we'll discuss in this lecture is parity. Parity is defined as a system wave function sign change if the sign of the space coordinates change. So if x goes to negative x, y goes to negative y, z goes to negative z. And a system has odd or even parity. Basically, it depends on whether or not that wave function is a mirror image or not. Parity is conserved, so it's something that we can use to evaluate how a property within a nucleus. It can tell us what reactions are probable. And for some of our considerations, nucleons in states with even angular momentum quantum numbers, so s, d orbitals, they have even parity, where states in odd L's have odd parities. And we'll use this more when we talk about determining spin and parity values from the shell model. And here's an overview of some of the data for elementary particles, particularly charge and spin information, and whether the statistics are Fermi or boson. Okay, within this lecture, we went over the role of nuclear mass in reactions, how we can determine reaction energies, how we can evaluate mass defects, how we talk about binding energies, and we even use this to develop some models. In some detail, we used these mass excess values to determine Q values. So you should be able to determine Q values for reactions. And we first explored some nuclear shapes, particularly potentials and how nucleons are distributed, that there's a half thickness and a skin thickness. And finally, we briefly touched upon some quantum mechanical terms that are used in the description of the nucleus that we'll use later in the course. Examples of questions you should be able to answer are shown here. One question is, what is binding energy? Well, that's the difference between the mass of the nucleus and the constituent nucleons. You'll find that the nuclear mass is not the same as the constituent nucleons. So if we were to take the mass of a proton times the number of protons in the nucleus plus the mass of the number of neutrons in the nucleus and subtract that from the nuclear mass, we'd actually see that we'd have a positive value. That's called the binding energy. You can think of this as what the amount of energy that goes into stabilizing the nucleus by taking the constituent nucleons and placing them together. What does this binding energy predict about nuclear abundance and energy release? Well, we looked at this graph earlier where we see the binding energy per nucleon. This is in mega electron volts, MeV, as shown here, as a function of mass number A. And we see this trend where this value goes up, it reaches a maximum, and then decreases. There's some relationships that one sees from this figure. One is that for relative abundance, the iron group, the elements around iron, are isotopes that are the most tightly bound, and they actually are slightly abundant in the universe due to this property. We also see that there's some energetic issues, and these relate to fission and fusion. For fusion, we see that combining nuclei up to iron releases energy. For fission, we see that splitting atoms that are above, let's say, mass around 120 releases energy. In fact, one of the things we see, this energy yield from nuclear fission, is due to this. If we take uranium-235 and split it from fission, we get nucleons that form in this area, and this gap here in energy is what's released. And we'll see when we talk about fission, around 200 MeV is released per fission event. Now, the other question is, what is the relationship between stable isotopes and the number of protons and neutrons? Well, we see that there's definitely a trend between the number of stable isotopes, which are shown here, and the number of neutrons and protons in a nucleus. Even nuclei, those nuclei with an even number of protons and even number of neutrons, have the most stable number of isotopes. Whereas odd neutrons and odd protons, those together, and odd nuclei, there are only 4 stable odd nuclei. And they are some of the lightest nuclei. Other questions you should be able to answer based on the lecture involve Q value. For instance, what is the Q value? Well, that's the energy defined as Q based on the differences between the parent and the daughter. Often we use the mass difference. We have a mass excess value where we convert the mass into energy. That actually utilizes E equals mc squared. How can one find the Q value for decay or reaction? Well, you can go to the mass excess tables, get the mass excess for the reaction, and then use that to determine the overall Q value for the given reaction. You can also use the Q value calculator from the web, and there's two that are discussed and links on the Canvas site that can be accessed. I will have an extra lecture for the Q value calculator. There are some bugs in the Q value calculator from Brookhaven National Labs. And if you're looking at a decay, you could actually look up on the table of the isotopes, that isotope and its decay. The table of isotopes will present the Q value data. Okay, how can one measure a nuclear radius? Well, generally scattering of charged particles. These charged particles can include protons, alpha particles, electrons. The energy in which one uses to probe the nucleus and the particle itself can yield different values for the nuclear radius. What are some other properties in addition to nuclear radius that can be measured with the nucleus? Well, nuclear spin and parity. Nuclear spin, as a chemist, one would be familiar with nuclear spin from NMR. Parity has to, like nuclear spin, is related to angular momentum, and parity we'll see has to come from the angular momentum state. Those that are even have positive parity, those that are negative have odd parity, and also the magnetic moment. Again, this is also related to NMR. Things like related to spin and parity, we'll a little bit with parity, but primarily spin and magnetic moment are used to evaluate chemical compounds from NMR spectroscopy. Please provide some comments on this lecture in the blog and respond to the PDF quiz number 2.